Hi Chem 140 students. So recently I made a horrible mistake while talking about atomic radius and the ionic radius. Basically this video is to kind of make up for me doing that, setting the record straight so you guys aren't as confused and can ace this next exam, which as you can see here I wrote down when your next exam is, and it is April 22nd, which is actually a Wednesday, not a Friday. So that was my bad. Okay. So along with this video, it's not just going to be ionic and atomic radius though. I decided to include all 7 trends of the periodic table, so let's begin. Right here I just have 3 definitions, arguably the most important definitions you'll need to know for the atomic trends, so either if you have a really good memory, just kind of try to remember them, or jot this down because it'll also help you when I'm explaining stuff next. Here I have color-coded all of the trends you need to know. First I'll start with the easiest, which is metallic and non-metallic character. If you understand this, then you can skip ahead a little bit. I'm basically just going to go in order though. So metallic character is in this black arrow here, and this arrow means that it's increasing. I set it up so all of the arrows are in the direction of increasing. So this black arrow showing that it increases. The best way to think of this is, so right here where my pointer is, these are the non-metals, so obviously metallic character can't be high with non-metals. So it makes sense that's the lowest here and higher over here. Now you guys may be wondering, well, why is it super metallic over here but maybe less so over here? You guys don't actually need to know the full science behind that. What I would instead recommend doing is kind of thinking about food in comparison to metal. Sodium is a part of sodium chloride, which is just table salt. You know, you can eat that. If you're thinking metal in your head, you're probably thinking less sodium and more so like steel, which obviously steel is a mix of metals and not like on the periodic table, but you get the idea. Now, if you go down here, which Fr is francium, if you are thinking about food, I highly doubt you're thinking about francium. So basically, the least likely to be in food is the most metallic. So after this, you have the non-metallic character, which is the complete reverse. So obviously all the metals are going to be a lot less non-metallic versus these non-metals here. But now you're probably wondering, well, why is fluorine the non-metallic? This is kind of similar to the thought process with the last one. So down here you have like phosphorus and sulfur and stuff. You kind of use this stuff in like everyday senses. So like chlorine you use in a pool. Sulfur and phosphorus you can use for like plants and stuff if you're really into gardening. So you're like, it's not a metal, but like it's an everyday use. Fluorine though, you're like, that's not at all a metal because like I eat it. Well, maybe not eat it, but it's like it's in toothpaste and a little bit of it's in our water. It's good for our teeth, that kind of thing. So think the most likely to be like ingested by you, but also like seems the least metallic, if that makes sense. So yeah, just remember those trends. They're a little bit easier than the rest of them. So then you have atomic radius. So I have atomic radius actually with increasing instead of decreasing here. Otherwise, this would be the smallest. So the reason that it would be decreasing and that fluorine would be the smallest is a little bit weird, because with atomic radius, it's not based on atomic mass or atomic number or anything like I said earlier, so again, I do apologize for that, for any of you that were in my tutoring session and heard me say that. So basically, the reason that it's increasing here and here has to do with electrons and protons. So atomic radius has to do with protons pulling on electrons. So basically, as you go across a table to the right, you're getting more protons. The more positive the nucleus is, or the more protons there are in the nucleus, the more attracted to the nucleus the electrons are, because opposites attract, and electrons are negatively charged. So if you have a super duper positive, or basically a super duper big nucleus, it's pulling all of those electrons inward, so it's like hugging them to its body, making its radius smaller overall, versus over here, it's not a very positive nucleus, and so it can't pull in the electrons as well, so what electrons there are not only aren't held in as well, but are able to repulse each other more easily. So that's why lithium's atomic radius is bigger than that of fluorine's. Now, when you go down, it's also increasing. This just has to do with shells. So basically, shells, or N, are represented by rows. So as you go down each row, a new shell is added. So even if there's more protons where it should be able to kind of like hold onto and pull them in tighter, once it gets to a certain point, it's like the electrons are so far away from the nucleus that doesn't matter as much. So basically, row trumps or like beats column. So if you're trying to figure out which one's larger for atomic radius, chlorine or bromine, even though they're in the same column, row beats column, so bromine has the bigger atomic radius. So again, your professor has it, the arrows pointing for the direction of decreasing. I have mine in increasing, and I swear that these are actually correct. Next, you have ionic radius, which I didn't add here. The reason I didn't add it is it's kind of weird, because if we go to the next slide, which is bigger due to ionic radius, Fe2 plus or Al3 plus? Basically, it all has to do with charge. So the more positive it is, the more it's able to pull those electrons inward. So for Al3 plus, for example, that means it lost 3 electrons, so it's 13 protons to 10 electrons. It's able to pull them in super tight and be a smaller size. So basically, when it says like, when it says that ionic radius has to do with charges, it just means cations versus anions. So it's the exact same trend as atomic radius in this sense. It would just be, instead of like this, these would all be ions with charges. So anions are going to be bigger than cations, which would be over here, just because you're adding an electron instead of removing. So that's adding to the shell and making it a little bit harder for that nucleus to pull them inward. And they're also repulsing each other more. So hopefully that makes sense now. And then that brings us to lattice energy. So lattice energy is kind of a weird one. So the way to define it, which I kind of did on this other slide here. So lattice energy is the energy needed to separate 1 mole of a solid ionic compound into its gaseous ions. So basically what that means is that higher charges and smaller ionic radii lead to a higher lattice energy. So that doesn't quite make sense, right? So basically what it means is this lattice energy can only relate to ionic compounds. And it means if you have NaCl, which is a +1 and a -1 charge, that has a lower lattice energy than MgO, because magnesium is +2 and oxygen is -2. So basically the charge, no matter if it's negative or positive, if it's bigger, it's going to have it's basically going to have a higher lattice energy. So that trend is here. So it goes up and to the right. And the reason for that is, so as you go to the right, charge is determined by column. So this is +1, +2, and this can be +2 to +5, I believe. It just depends on the transition metal, and it will be specified to you, but they're a little bit weird. So obviously that's a super high charge. So that's going to be, so if you had, for example, let's say you had iron +3 with something, that's going to be stronger than something over here. I know you guys might be wondering, like, well, it makes sense that it goes from left to right, but why does it go up or down to up? The reason for that is it just has to do with electronegativity, so it literally just matches that trend. So basically, since lattice energy is the ability to form a gas. For you to be able to form a gas, you have to be able to break up the molecules, and that's easier to do if electronegativity is higher. This brings us to our second to last one, which is electron affinity. So electron affinity is just, think of it as either the tendency to gain electrons or energy released from adding electrons. So as you can see by this pink arrow here, it's pointing to fluorine, so it's basically the exact same trend also as the lattice energy. But the electron affinity, since it's talking about gaining electrons, has to do with anions, because a negative charge, or an anion, is from gaining electrons. So if it's talking about energy released, if it's super easy to add an electron, or it doesn't require as much energy to add an electron, that means that more energy can be spent or released. Hopefully that makes sense. If not, you can totally talk to me either in tutoring or just like leave a question in the comment section or even shoot me an email. So this brings us lastly to ionization energy, which is the exact same trend as electron affinity, or it's not like the same definition, but basically it goes the same direction. So fluorine also has the highest ionization energy. And the reason for that is ionization energy is energy required to remove an electron. So as we already discussed, this section here does not like to have electrons removed, it likes to gain them. So anything that's an anion, the ionization energy is going to be super high because it's harder for them. It requires more energy to force an electron on them since they're so ready to accept one instead. I hope this helps. So that brings us to slide 4, which is the last slide of this video, and this is just practice problems. So why don't you guys just take a minute and see how you're doing, pause the video. Alright, I'm going to assume that you guys pause the video and work through these, so here are the answers. So I'm going to very quickly kind of go through and explain why these are the answers for each one, and I'm actually going to start over here. So I know that ions are included up here, but basically if you're looking at a periodic table, so you have Fe, which should be right here, and then you have aluminum right here. So since aluminum is in the third row, also it says the atomic number, but since it's in the third row while iron is in the fourth row, automatically aluminum has less shells as well as less protons. So basically, it is able to, once it loses 3 electrons, it has 10 electrons and 13 protons, so it's easily able to like pull in all of those, very few honestly, electrons and make a very small atom, while iron over here would be losing 2 electrons, so that would bring it to 24 electrons for 26 protons. Now technically it would get a little bit smaller than just overall iron, but it's still going to be much larger than Al3+, because it was already bigger. It already has an extra shell and kind of has to like reach farther to bring those electrons into it. So again, row beats column. As for which of the above atoms has the lowest ionization energy, for that one it's hydrogen, and you just have to look at the trend. So on this you go to ionization energy, you look at the arrow and it's pointing over here. It makes sense that hydrogen has the lowest ionization energy because hydrogen is already kind of unstable. It only has 1 electron and 1 shell. So by losing an electron and becoming a positively charged ion where it's just the positive nucleus, it's actually more stable because it's a really, really weird atom. But in case you don't want to have to know all the science stuff behind it, just memorize this trend here, which is this darker pink arrow. So it's basically saying that to the right and down is the most ionization energy required. That brings us to this last one here, which is rank the atoms in order of increasing atomic radius. Start with the smallest. So atomic radius, if we go back here, is kind of weird because I know it's saying like it's increasing this way. Technically, this arrow should end right about here because hydrogen is actually the smallest with atomic radius, which is weird to say. Like I said, hydrogen just kind of does its own thing. It's a very interesting element. And then as for the rest of them, you kind of just follow this trend for increasing. So you're ranking these. So basically look for the one that is the farthest down and most to the left. So in this case, that is iron. Otherwise, since oxygen is smaller, it goes hydrogen, oxygen, nitrogen, carbon, and then iron. I hope this helps. And if you guys were like, oh damn, I did really bad and I didn't get any of these practice problems right, that's okay. Just keep practicing, like do your homework, come to more tutoring, even go to office hours with your professor if you think that'll help. So have a good rest of your day.